Welcome back, and now we get to move on and talk about another test that we can use for convergence and divergence, the comparison test. Okay, now this is, you can see it on the screen already. It looks very, very similar to what we saw with improper integrals and their convergence. And actually, because of the connection we made with functions and sequences back in the first video when we were talking about the integral test, that's kind of why the comparison test works. Now, the full proof is in the text. I encourage you to look through it. It is very, very useful, so refer to that. But the idea is that we have two sequences, an and bn, and we know that an is less than or equal to bn, and then now we're going to look at their associated series. So we would say that if we know the bn is convergent, the larger one is convergent, then the smaller one is convergent. So that's how I remember this, is if we converge above, then the smaller one converges. Similarly, if an, the series, which is the smaller one, diverges, then the larger one diverges. So if we're looking at convergence, we have to have convergence above to prove convergence of the one we're interested in, and if we have divergence of the smaller one, divergence below, then the larger one is also going to diverge. Okay, so we just want to go through a couple examples here. I'm going to do one, and you're going to do the second. So is this first one going to converge or diverge? Now, with the comparison test, the trick is to sit and stare at it for a long time and just think to yourself, okay, what's your natural intuition? Like, do you think it's going to converge or is it going to diverge? Like, you might have to play with numbers, that sort of thing. And again, remember, we're not just looking at a sequence, we're looking at the series, so it's a sum. Is the sum going to converge? Well, and then after a while, you say, okay, I'm just going to try some things. So with comparison, we need to use a string of inequalities, and you want to compare the sequences, not necessarily the sums. But if we look at the sequence, n plus 1 over n squared, my intuition says that this looks, for very large values of n, like 1 over, let me do it over here. I'm thinking in the back of my brain, this looks a lot like the series 1 over n for very large values of n, and I know this is divergent. So if I have that intuition of divergence, again, I need divergence below, so I want to make this what I have to be bigger than whatever follows. So I need to make this whole thing smaller. Well, certainly if I subtract 1 from the numerator, that makes the whole thing smaller. Okay, and this is 1 over n. Okay, now with this series, I have to say that 1 over n from n is equal to 1 to infinity diverges by p series, or really you could say it's a harmonic series. Either one is sufficient. Okay, and then I'm going to say and series of n plus 1 over n squared is bigger than series 1 over n. Thus, the series n plus 1 over n squared diverges by the comparison test. And that would be my full conclusion. Okay. Now, technically, there was a component that I did not check that I really should. I need to confirm that the sequences are all positive value or contain all positive values. In most cases, when you're working with natural numbers, it works, but just be aware and have that on your radar. Okay. So now I want you to pause the video, try this one, and determine if that one converges or diverges using the comparison test. And here's my solution. So when I did some thinking about this, I thought it looked a lot like 2 to the n over 3 to the n, which I could also write as 2/3 all to the n, which is a geometric series, and I know that that's convergent because the common ratio is less than 1. And so now I just went through and showed that, recognizing that if I subtract something from the denominator becomes smaller, which means I'm dividing by an overall my whole expression becomes larger overall, so then that's where I get my convergence. And then I just go through the formal language to conclude convergence. Okay? So, big ideas here with the comparison test is you do have to satisfy that condition of having positive sequences. That's generally always true. But then, again, I remember this, you have to have convergence above to conclude convergence, or you have to have divergence below to conclude divergence. So make sure to be careful in your choice of comparison, sequence, and series, and then use the comparison test appropriately.